The following podcast is a proud member of the Blue Collar Roots Network. Find all the shows by visiting bluecollarroots.com.
When you hang out on the playground, some kids like to talk about Harry Potter and others are into Star Wars. Bill was the kid in the corner talking airflow. Here's your host, Bill Spohn.
Welcome back to another edition of the Building HVAC Science Podcast. Having worked in the HVACR and building performance markets for almost 30 years, I've noticed the need for scientifically rooted information to help people do a technically correct job. And I've teamed up with the folks at the Blue Collar Roots Network to do this, to communicate with you through this podcast. There's some other great podcasts in the Blue Collar Roots Network, the Tool Pros podcast, the Service Business Mastery, and of course, the groundbreaking HVACR School podcast. It's a really great series. Brian does a remarkable job keeping the information flowing with that. After listening, if you like what you heard today, I'd encourage you to subscribe by typing Building HVAC Science into a search bar of any of your podcast apps on Apple or Android, Google Play Music, or Stitcher. You can also listen, if you wish, anytime in your browser at bluecollarroots.com/building-HVAC Science. Now, on to some learning about airflow. This will be part 4 of my lessons, AirQuest 2016, 2017, 2018. It's just an AirQuest. It just continues to go on. So here you go. Take a listen. Thanks. Now to recap, we've been covering different methods of airflow measurement. We covered hot wire anemometers last time and the importance of probe placement when you're making or doing a traverse. Next up, I'm going to cover an airflow measurement that gets its roots from the work of Leon Battista Alberti, who's said to have invented the first mechanical anemometer around 1450. Now his design embodied horizontally spinning cups, if you can imagine that. You've probably seen these in outdoor wind speed meters, spinning cups on a vertical shaft. Now numerous others, tried to improve on the design over the centuries, including Hooke, Robinson, whose design had 4 cups, and Patterson, who developed the 3-cup anemometer. Now the simple elegancy of this design is that the airflow past the cups in any horizontal direction turned the shaft at a rate or speed proportional to the air or wind speed. Note that the first main use of the design was in measuring outdoor wind speeds. So the shaft turns are counted in RPMs, and via calibration in a wind tunnel, the result is equivalent to the air velocity. Now, you've probably seen one of these cup-type airflow meters at a small airport or a farm or an outdoor environmental station, even sometimes along the highway. And one key element is the tail. And that tail, due to the Bernoulli pressures, have I failed you by not talking about Bernoulli pressures yet? Well, we'll have to get to that sometime. Those Bernoulli pressures keep the cups pointed into the wind stream. Getting to the vane anemometers that we see in HVAC, you notice that they contain propellers which face directly into the wind stream, thus eliminating the need to hold it perpendicular to the flow like the cup with the tail design. But this design mandates that you're directly facing the vane into the airstream, and there's no auto positioning like the cup design, so it's up to you. There's human intervention required to get this thing squared up and facing straight into the airstream. Now luckily, the designs of these modern anemometer, the vanes themselves, are tolerant to being off axis by about 10 degrees, but you can check your position to make sure you're getting the max value, as that occurs when you're properly aligned with the airstream. The max occurs, of course, when you're capturing as much flow as possible and getting that highest velocity, highest RPM on that wheel. Now, the first vane anemometers use mechanical linkages from the shaft to a dial or some kind of counting apparatus. We all know that mechanical means physical components, and physical components usually have mass, and mass means there'll be inertia. And I know I'm getting all sciencey and engineering on you, but this is just the facts. There can also be gear train slop, where the gears fit together, which will factor into making some of these first designs being less than ideal. And in some people's minds, vane anemometers still have those kind of mechanical inertia, slop kind of limitations, which make people think vanes are inferior. But science has marched on, and we got some new vanes today. Many of the new vane anemometers today use man-made jeweled bearings to minimize the rotor friction, and also a photocell or an inductive pickup that counts the revolution. So a contactless pickup. There's no gears anymore. There's no linkages. There's no shaft or dials. It's just a spinning wheel, spinning free in the airflow, and somehow the revolutions are being counted. So this detection method yields a much cleaner measurement. Now CFM, cubic feet per minute, or volume flow rate, can be calculated once you have the airspeed from the vein and you plug it into a formula with the cross-sectional area, basically multiplication. Your cross-sectional area is in feet squared. Now when properly used, the rotating vein anemometer is really highly accurate and a quick measurement, and it's often the best way to measure airflow. Vein anemometers have several advantages over any other method, and some of the primary advantages are speed to make the measurement, accuracy, and ease of use. Vein anemometers don't require air density compensation due to temperature, humidity, or atmospheric pressure because they're measuring the airspeed directly. Now, vein anemometers do have a little bit of mass to them, so you do have to be cautious when you're making a measurement that there isn't a rapidly changing phase or flow velocity field that you're measuring across, in which case the vein might continue to be turning from where you last had it versus where you have it now. So there has to be a speed of measurement which has to be controlled for the velocity of the airflow that you have. There's even some mini vein designs on anemometers about 1/2 inch in diameter that allow for a full in-duct traverse with an automatic calculation of the CFM in the duct if the dimensions are input into the instrument before you take the measurement. Now it's important that the ducting is attached to the appliance and the base pan, if there's a side return being used, that's sealed, that you have everything all sealed up so you aren't squirting any air outside of the ductwork. And a large vein can be used to measure at registers to proportionally balance the system or for accurately measuring airflow at a return. At a supply, a vein is, again, kind of tough, not due to the fact of the vein, but due to the fact that you probably don't have an accurate open area measurement available to you. If you do, you're in luck. You can just go ahead and use that vein all day long. But if you don't, then you're making a guess and you're going to impact and add error to your readings. Usually the heads on vein anemometers for supply and return airflow measurements are about 4 inches in diameter, 100 millimeters. Sometimes they're 3 inches. The large size head intercepts a larger area of the fluctuating airflow streams or jets, thus it automatically averages velocity, and via the calculation automatically averages your volume readings, your CFM. One of the challenges that is relieved when you use this kind of device is they operate pretty much independent of air density, like most other air velocity measurements, because they're directly measuring wind speed. And as we mentioned before, one of the challenges that comes in is the physical mass of the vein, or the inertia, needs to be accounted for in situations where the airflow is changing rapidly. You need to move slowly enough through a traverse to let the vein come up to or drop down to the correct speed. Another challenge comes from rotating air, or swirling or spinning air that hits a vein and causes it to speed up or slow down due to the swirl or rotational energy and not actually the airspeed. Now to overcome this, one of the manufacturers, Testo, makes a unique attachment for their Model 417 vein anemometer, 4-inch vein. It's essentially a long tube which allows for the airflow to kind of calm down, an internal grid to quiet the air and remove the swirl. It's actually a grid at both ends of a tube that removes the swirl crossing the vein, so it straightens things out, makes a more laminar flow. And the measuring range limits are dictated by the design of these veins, so you need to check with your manufacturer or your technical sales rep, wherever you're buying the products, to make sure this device does what you intend it to do. Test equipment for vein anemometers can range pretty widely depending upon size of vein, various features, from $50 to $600. The time to set up and make a test measurement is about 15 to 30 minutes, depending on if you're doing in-duct testing and you have to go back and plug the sample holes, create and plug the holes, or it could be less time if you're just measuring at a return. Tests at supplies and returns can also be done pretty quickly, but again, supplies, you need to know that cross-sectional open area. At returns, you don't need to know the open area because the airflow is coming from the room into the device and then into the grill. Mini vein anemometers are used for in-duct transverses exclusively. Large vein anemometers are used for grill traverses in supplies and returns. And again, on the supplies, make sure you have that open area. Some large veins have accessory scoops, or some people call them mini hoods or flow funnels for low flow measurements. Emphasize, you must read the directions. These mini hoods or scoops are limited to very low flows, often like around 50 CFM. And I've seen test data from a very controlled lab conditions that shows the error can be 30-40% if you use them outside of that spec, outside of the range they're supposed to be used. So you can get numbers, but they're not good numbers. They cause back pressure, they cause this insertion effect which will cause an erroneous reading to come up. And as we mentioned a little bit earlier when we talked about capture hoods, there's the CPS Easy Hood, which uses a 1-inch mini vane. It's a hybrid between a capture hood and a vane anemometer. This mini vane is centered in a small hood. It's preceded by a flow straightener, which irons out the turbulence. Now, this compact, low-cost device can measure from about 7 to 1250 CFM, and the price point at this point is around $400 for the full flow hood itself. Okay, let's move along and wrap up a few other types of airflow measurement devices in our discussion. First, let's go beyond capture hoods. Capture hoods really don't capture, but they're more correctly deflector hoods or transition hoods, as their purpose is to move the airflow through an area of known cross-section where it gets measured by a measuring array or probe, maybe a mini vane of some sorts. Now, the only true capture device that I know of, or tool, is called the bag inflation device, better known as the garbage bag method. Bear with me here. Don't shut this off. Don't press stop. Don't change the station. We'll talk about this. One huge limitation to this method is the fact it can only be used on supplies. I can't imagine a practical way of deflating a bag full of air placed over return. Can you? So this is only a supply type measurement. And before you dismiss this topic as junk science, and that's not going to be the name of a new channel or podcast, I'll take a moment to consider the extremely simple act of capturing air in a container, the bag, of a known volume, or cubic feet. All you need to know is figure out how long it takes to fill the bag in minutes, and voila, there you have it, cubic feet of air in a bag, or CFM, cubic feet of air. The drastic simplicity of this method makes it a very good hands-on teaching tool to understand many aspects of measuring airflow. And the required equipment is easily and inexpensively procured, a plastic bag and a stopwatch, or likely you could use the stopwatch function on your smartphone, which is probably more accurate than a regular stopwatch. Let's unravel this method for the assumptions and challenges it presents. Because if you haven't heard it before, I'll repeat again what Jim Bergman preaches. Estimating airflow is easy. Measuring airflow correctly is difficult. Now, the first challenge is accurately determining the time of inflation. If the bag is small, tenths of a second can make a difference in the calculation for this bag inflation device. For example, when measuring airflow of about 150 CFM, a 38-gallon bag, which is about 5 cubic feet, which is your typical large garbage bag, will inflate in about 2 seconds. But if you have a cumulative error of half a second in deciding when to start or stop the timing, or if you have a jittery trigger finger or a sloppy technique when placing the bag on the grill, you can cause an error of plus or minus 35 CFM in the final value. That's plus or minus 23%. Now, another factor to consider is the actual weight of the bag when used on any grill that's attached to a finished surface except a ceiling. The weight of a hanging bag impedes the airflow and causes back pressure as the air inside the bag has to lift to fill the bag. So lighter weight bags are better. Now, choosing a larger bag diminishes the criticality of the time measurement, but a larger bag may be heavier. Or if you find a larger lightweight bag, you might know exactly the volume that it holds. And you might just say, oh, just fill it with water. Well, yeah, go ahead and try that. Good luck, because the weight of the water is going to likely tear the bag as it fills and become quite a problem if leaked. Now, I credit Gary Nelson, who's the former president and owner of the Energy Conservatory, with an answer to this conundrum. How do you tell the volume of a plastic bag? And simply fill the bag with packing peanuts. Then dump the peanuts into a rectangular box where you can measure the height, the width, and the depth, and you can actually get the cubic volume of peanuts that formerly filled the bag. It's probably going to be pretty close, and close enough for this method that we're using. Something to keep in mind is what I call the Eisenberg uncertainty principle, or the process of measuring airflow changes the result measurement. Insertion loss or squishiness of air. I call it all kinds of different things. In this case, as any pressure develops inside the bag, the supply airstream that's trying to fill the bag is going to feel this pressure and begin to slow the inflation of the bag. So if you limit, it would then limit the quantity of air entering the bag. So a simple way to determine this is to watch for the bag getting full. But how full is full? A slick way around this might be to take a pressure tap, a static pressure tip, tape it inside your bag, poke it through, and tape it on the outside of the bag, connect it to a digital pressure meter, manometer, that can read low pressures though. It's got to read like in thousandths of an inch of water, or pascals. So immediately when that pressure meter shows a spike in pressure, you can say your bag is full. You just increase the cost of your test equipment from pennies to $450 or so to get a decent fine resolution pressure meter, so you may want to kind of rethink this whole scenario. But again, I think it's a good teaching lesson, or at least a good thought lesson. Now, interestingly, this method, the bag inflation device, was actually written into an ANSI standard. That's ANSI ResNet ICC 380-2016, which the title of the standard is the standard for testing airtightness of building enclosures, airtightness of heating and cooling distribution systems, and airflow of mechanical ventilation systems. Now, this is in section 5.2.2, and you can download this full standard if you're curious. It's free of charge at this link, which is www.bit.ly/ these are all uppercase letters, ResNet-380, ResNet 380, all uppercase. Now, no manufacturer currently makes an ANSI 380 BID, bag inflation device, but you can make one of your own following a recipe that's actually given in the standard, and I'll give you a quick overview of that right now. The BID, bag inflation device, actually has a lightweight box or even a wood or wire frame which must contain an airtight perimeter seal to seal against whatever textures are present by the surface over which you mount the bag inflation device to access the supply grill. And there's actually a video of doing this, which I'll read in a moment, the link to that in a moment. The BID was created for use on the exhaust ventilation fans, so the surrounding siding treatment sometimes presents a sealing issue. The plastic bag must be of a known volume, and we just recently mentioned there that Gary Nelson helped us solve that challenge. And the test frame or box must hold the bag open, thus overcoming part of that weight of inflation issue. There should also be a shutter which controls the airflow into the bag to start and stop it. That helps with the start-stop timing. And the thickness of the bag should be selected that 3 or more measurements of a single terminal produce results which are in 20% of each other. That means that each person that makes a different device must do their own testing to determine this factor. Okay? Now, the volume of the bag chosen must fill within 3 to 20 seconds. So our 150 CFM supply filling in 2 seconds with a 38-gallon bag already violates this rule. Trigger fingers aside, it's going to be hard to make that timing measurement, so a larger bag must be chosen. So if you'd like to see the bag inflation device in action, it's actually a video sponsored by the EPA Energy Star program, which is an explanatory video which can be viewed at this link, www.bit.ly/380-BID. That's 380-BID for bag inflation device, all uppercase letters. bit.ly/380-BID. Thanks for listening to that episode of AirQuest. That's AirQuest Volume 4, Chapter 4, whatever you'd like to call it. If you want to keep up with other things that I find interesting, you can follow this channel on Facebook by typing Building HVAC Science into the Facebook search bar. You'll see a lot of other links to other things that we find interesting. I'm going to share with you a quote for the day. I like this one. It's by Ernesto Bertarelli. You can't change who you are, but you can change what you have in your head. And you can refresh what you're thinking about. You can put some fresh air in your brain. I like that. Fresh air. Talking about airflow here. So if you're looking for any of the tools or test instruments we spoke about in this episode or any of the previous episodes or any of the podcasts, you can take a look at what TruTech Tools has to offer, TruTechTools.com. You can use the code HVACBS, and that BS stands for Building Science, for a nice discount. In full disclosure, I'm a co-owner of TruTech Tools. Thank you for listening and following and hopefully subscribing to us. Clicking on subscribe will ensure that you get up-to-date issues that are pushed right out to your device to listen to and keep up with what the building HVAC science world has to tell you. Thanks again, and have a great day.